Great. So we'll go over to, reinforcement learning and causal reinforcement learning, as was briefly brought up by Elias. So very excited to have Uri Shalit here from the Technion. And Uri, it's all yours.
Okay, thank you very much. Thanks for inviting me. And I'm really sorry I couldn't be there. Hopefully we'll get back to traveling soon. So let's talk about what motivates this, the research I'll talk about today. So we're thinking about tasks like autonomous driving or robotics, or maybe in the future, medical treatment, which we'll like to learn automatically, where there are many actions, there are long-term dependencies and high-dimensional state spaces. So kind of difficult AI tasks. And in such tasks, learning online is crucial. And because we all know the problems with offline data, confounding and all that. And for such complicated and high stakes tasks, we have to do some online learning. And in a sense, learning online is optimal from a causal perspective. Elias has a lot of work on that kind of problem. But as we also know, learning online is often expensive. It might require a lot of money or people or time to do that. So a natural question is, can massive offline data help by saving us money or interactions or mistakes that we could have avoided if we've learned from offline data? And specifically the scenario I want you to have in mind for this talk is that we're learning online, but we have access to large offline data. For example, it could be logs from driving or human demonstrations of robotic tasks and so on. And the challenges we'll address in this context is basically where there's some mismatch between the offline data and the online environment. For example, we might have confounding, we might have partial observability, we might have distribution shifts. All of these problems, which are realistically, we will have to face if we're learning in this online situation. Sorry, just need to do something here. Okay, this is. Okay. Oh, sorry, still not good. Okay. So if we want to learn online with some offline data, there's some very obvious baselines. So just so we're on the same page, first we could just ignore the offline data. We're assuming we can learn online, so we can set our autonomous car driving or our robots training. And this is most of Bandit and reinforcement literature is about this setting. The other option is we can just ignore the online data and just use the offline data. And that's the realm of off-policy reinforcement learning, for example. And this is vulnerable, for example, to hidden confounding and distribution shifts. And sometimes proxies might help. We and others have some work on that. But generally, it's difficult to just use offline data, especially if you have large action spaces and complex state spaces. And in this talk, we'll talk about how to merge this offline and offline data in challenging scenarios. And of course, we're not the first to do this. There's other work as cited here and much more. Okay, so I'll talk about two specific projects. And let's just start with the first, which was presented as a paper in UAI 2021. And this is in the realm of bandits. And specifically, we're talking about the linear bandit interaction model. So I'll go over this model briefly. I assume most of you have seen this. So we have rounds T, one starting from 1. We observe some context X from some distribution. We take an action, which is a function of X, out of an action space, a discrete action spaces of A actions. We get some noisy feedback or reward, which we assume is an inner product between the context and some optimal unknown vector W star AT plus some noise. And we get some regret, which is the difference between what we chose, the A that we chose, AT, versus the optimal A. And of course, if we know all the vectors W star, then we can act optimally, but we don't know them, have to learn them online. And we want to minimize cumulative regret. So over the rounds, minimize this regret. So the optimal action is context dependent, but there's no state. So there's nothing carrying on from round to round. We have these classic explore exploit trade-offs here. And usually the goal is to get sublinear regret, often some O of square root of T times all kinds of constants, which depend on the dimension and action space size and so on. And large T is just the number of rounds or interactions or actions we can take. And we assume, in addition to the classic online linear bandit, that we have triplets of historic data in the form of context, action, reward triplets. Now, if this historic data is fully observed and there's a complete match between the offline and online setting, we can use what's called sometimes learning from logged bandit feedback, or just classic observational study techniques, and use that to initialize online bandits. But we're looking in a slightly more challenging setup where the historic offline data is only partially observed. So let's say the actions we have in the historic data were taken by humans, and humans perceive differently from machine. Or maybe it was just not fully recorded at the time. That often happens. Like even Google, which uses contextual bandits online, it doesn't always record all the data that went into the decision of their own algorithms. And maybe there might be privacy constraints that we just cannot have access to all this data because some of it is private. Okay, so the model we're thinking about is as follows. So there's this environment. It generates this vector that we see of context, for example, describing the user. There is a policy, pi_b, which generates an action. There's this vector, WA, which corresponds to the action. And what we see is this inner product plus noise. And this vector, the red thing, is part of the world. And in general, this just goes on and on. And if we had fully observable data, we would have seen all these triplets X, A, R. But we assume partially observable data. So part of the X vector, part of the context vector used to make the decision and used to get the reward is hidden from us. We don't see this in the historic data. We only see it when we play online. Okay, and we'll decompose this vector X into the observable part XO and the hidden part XH of dimensions L and D minus L respectively. And we assume the offline data had some policy pi_b of A given X. Now, if we make no further assumption, the offline data is almost useless, right? Maybe all the important information is in the hidden vector and it has no correlation with the observed part of the vector, and then there's not much we can do. So we have to assume something else, some extra assumption to make this useful. And specifically, so we go beyond like the classic bandit literature and the causal bandit literature to kind of this merging. And we first just have this general bandit result, which is bandits with linear constraints, which like has not been explored before, maybe because there weren't many uses for that. But what we show is that bandits, where we have some linear constraints known about the rewards, we can actually translate this problem, the problem of using offline data, to approximate linear constraints. And I'll give you kind of a hint of how we do this in the next few slides. Okay. So what can we say? Let's look at the least squares estimator for the reward given any particular action. So this is using only the observable part of the vector. So we know this is the best estimate we have. We also know it's biased because we only regress the rewards on the observed part of the vector. So this relates to kind of misspecified OLS models, like going back to the 50s. So we denote this regression by BLS, least squares, for a given action. We have it for any given action, this vector B. And B is learned, we can estimate it from the offline data. And now we define these two correlation matrices, ROO and ROH, which are the covariance of the observed axis and the cross covariance of the observed and the hidden axis. And we can show that in the limit of infinite data, and assuming the observed covariances are invertible, then this vector BLSA has this nice structure, which is like this rectangular matrix of the identity matrix, RO minus 1 times ROH times the optimal vector W star A, which I remind you, we would like to know W star A ideally for every A. Now, okay, so this is just a kind of linear algebra result, basically. How can we use this? So we have some observable consequences. So for every action A, we have this vector BLS, and we have this matrix which we denote MA, which, as I said, is just this rectangular matrix with this nice structure. And if we had known M, we could have used the pseudo inverse of M and just project our estimate W star A to this pseudo inverse M times BLS, because we know we have to obey these constraints. So we can just repeatedly project onto this constraint that we know must happen from the offline data, again, assuming infinite offline data. And if we had known this, we can reduce regret from a kind of O of D times square root AT to O of D minus L. So we reduce the dimension basically by the dimension of the observed part of X. And we get improved regret. The problem with this is, of course, we don't know M, because M has this nasty part. So we get BLS and ROO minus 1, but we don't have ROH. Okay? The correlation of the observed and hidden data is hidden because we don't see the data, right? The hidden data. So we would like to use these linear constraints, but we can't because there's still this hidden component. So here is the part where we must assume something. We must assume that we can have some way to estimate this hidden part, ROH. And we can make all kinds of assumptions. I'll talk about one. We have a more general result, but here's one assumption, that during online operation, we can query the behavioral policy. So it's not like we see the hidden components and we don't know exactly the policy, but at every round, we can ask the behavior policy, what would you have done here? We don't have to act the same, but it assumes we have kind of access to that model. And as usual in causal assumptions, you can argue when and where are they plausible or not. And I just want to say this similar to Jung and Barenboim's notion of intuition from their 2016 paper. And we show that if we can do this, we can actually approximate the pseudo-inverse MA, which is generally difficult because pseudo-inverse is not a continuous operator, but because it has a special structure, we can do that. And then we can prove this result, which is a sublinear regret, where we save, again, this D minus L. So we reduce the constant factor here by exactly the dimension of the observed part of the hidden, plus some extra factor. And this extra factor basically says how hard is it to estimate the linear constraints. And it's related to how uniform is pi b and how well conditioned are these matrices. So all the kind of funky stuff goes into this factor. And just very roughly, we can say that in the worst case, this bound is meaningless. It means there's no point in using the offline data. In the best case, we can get actually improved performance, though still dependent on D. So it really depends on the details of how much is the hidden part of the context vector important and how well is it correlated with the observed part. So in the good scenario, it's really useful. In the bad scenario, it's still basically useless, even though we assume this sampling from pi b. Okay, so this is one result about using offline data and kind of getting faster convergence, right? So in the good scenario, we can use less interactions to get at the optimal reward using this offline data. Okay, so this is for the contextual bandits. And now I want to talk again briefly about a slightly more involved scenario of reinforcement learning. And this is a paper just accepted to iClear 2022. And now we'll talk about this more complicated scenario. And we'll talk about imitation learning. If I were in the room, I'd ask people to raise their hands if they heard about imitation learning. Maybe could someone tell me for a raise of hand, how many people are raising their hand, roughly, have heard about imitation learning?
About 15.
15 out of, I don't know how many people are in the room.
I'm so bad at estimating. So maybe that was about a fifth of the people in the room.
Okay, so most people haven't heard it. Okay, so imitation learning is this idea in reinforcement learning, which is really straightforward. It says reinforcement learning is about optimizing the reward and so on. But if we have someone demonstrating to us how to do something, we just learn to imitate them. So just learn what action would they do at any given instant. No reward, there's no reward in play. And this basically reduces to a supervised learning problem. So you just learn when this is the state, do this action. And then if you manage to solve this problem, if nothing changes and everything is all right, then you can do as well as the demonstrator, as well as the person you're imitating. Okay? And this is actually widely used, especially in tough reinforcement learning problems. So for example, DeepMind had this StarCraft model Alpha Star, and they used just imitation learning from human players to initiate it, and even that already broke the state of the art. They then built like reinforcement learning on top of that to get even better than that. Okay, so basically it's kind of reducing it to supervised learning, but there's a lot of work on that in recent years in the RL community, how to do imitation learning better. I won't get into that specifically. And again, we're kind of challenging them all. We're saying, okay, but what if we have partial observability? Again, if we're thinking about, let's say, a model learning from human drivers, like learning how to drive using human drivers. The human perceives things that the machine does not. And we have to account for that. And moreover, maybe the data was collected in some different environments. For example, if we're looking at recommendation systems, maybe the product changes all the time, what's available changes, customers change. So again, we're learning from this offline data from an expert, but it was in a different situation. And again, privacy constraints might also be something that we have to deal with. So let's see, how much time do I have?
15 minutes. Oh.
Okay, I'm good.
A bit less.
A bit less. Okay. Stop me when you need. So again, so we move for bandits where you have like an X at every time, and that's all the context, and just the action interacts simply. Here we have a more involved situation. So we have a classic MDP markup decision process where we have a state and an action, and oh wait, there's a like A here is action space, not state space. I'm sorry, this is just a mistake. And we also have a context space. So maybe this will be easier for people in this crowd. So we assume a state and there's an action, and then we get the reward, which again, we might ignore in imitation learning. And then the action also gets us to the next state, which is a function of the previous state and the action, and so on and so on. But in addition, there's this X. You can think about it as a categorical variable, which says, okay, but everything might change based on context, right? So driving in the snow is not the same as driving in the desert, or like recommendation system in 2019 is not the same as 2020 because many things change. Okay, so this is the model we'll assume. And we'll look into cases where X is not necessarily observable, and also the distributions on X might change. Okay, so we assume we don't see the expert's reward. That is usually the case in imitation learning. We're just trying to learn their actions. We assume they have some optimal policy pi star, which is a function of both the state and the context, but we don't see the context. Okay? We don't know the context they use. We only see their states and actions. Okay, so this is one way to model this partial observability situation. And further, we might have different distributions over X between the expert situation and the online situation. So here E is expert and O is online. So it's a form of covariance. And there's a standard reinforcement thing value, and the optimal policy will be the one that maximizes value. And we'll have like the set of maximizing policies, the optimal policies that we would like to enact, but we can't always do that. So we have the expert policy pi star. So that generates a trajectory. We see like the driver driving and so on. However, we don't get to see X. Okay, so we just see these kind of state action, like what happened over time. Okay, these kind of histories. And they have a probability in the offline data, in the data we get from the expert. And what's written here is just like standard probability theory, nothing special, just decomposing the distribution. But note that this is a mixture with some probability over the context, which again, we will soon assume might change. And we don't see this X. Okay, so we have this mixture of things, but we don't know the mixing coefficients, and they might change. Okay, but this does generate this distribution over the state actions. And this is kind of the information we have. We know the traces, the state action traces, and we have the environment, like we're acting in, that our agent is in. It has their own traces, and the expert has their traces, and they might or might not match. And what we define is this ambiguity set, which is the set of all policies. So this is it over policies. All policies which generate the same state action distributions. And again, these are our observables. So this is what we can do. And we cannot basically differentiate between policies in this set. We cannot, if any policy in the set, if it induces the same state action distribution as the expert policy, that's the best we can know. And what we can show is that any policy in this ambiguity set can be an optimal policy, and we can't rule them out using state action frequency distributions, but some might be suboptimal. So like this is the best we can do, but it's not great because some of these policies might not be the optimal policies, and there's no way we can know this, even if there's no covariance. Okay, so this is first result, which says this problem is a bit hard. We're not seeing the context, and this makes our life more difficult. Or it might make our life more difficult. We have an algorithm for this situation, which kind of we can prove is not terrible, kind of proves it's not we can do better than the worst, but we can't prove much more about this. I won't talk about this out. We then say, okay, let's make this a bit harder. We not only don't see the expert context, but we assume covariance. Okay, so the expert works under some distribution of the context. We work under a different distribution. We assume they overlap, that there's kind of common support. And what we show is that if the transition probability is independent of the context, then the worst case policy cannot be ruled out. So this might seem counterintuitive, but it says if the contexts don't affect the state transitions, that means basically we have no clue what's going on, because the state transitions are our only view on the policy. So if they're independent of the policy, then we're in complete dark and we have kind of nothing that we can do. So that's actually the worst case. On the other hand, we have kind of the best case, which says if the rewards are free of the policy, of the context, sorry, then basically we can do well. And this basically says there's no confounding. If the context doesn't affect rewards, then we're in a good situation. So there's this kind of spectrum of options, okay? If the reward has nothing to do with the context, then imitation is actually, even confounded imitation is possible. Imagine this kind of maze, and imagine we've seen people acting on the maze without seeing the walls. It seems, and let's say in the expert used one wall setting and we're in a different setting of walls. But if the goal is just to get to the left side, we can still learn from the expert that just moving left is good, even if we don't see the details of the walls. And surprisingly, that's kind of helpful. As we said, that's like one side of the equation. The other is if the transitions have nothing to do with the context. So we have this example which says like there's complete impossibility of imitating successfully. I mean, we can imitate, but it will be catastrophic. And there's all the middle, okay, where the reward and the transition are both context dependent to some degree. And we have a kind of a sensitivity analysis for this. And that means in those cases, imitation is possible, but biased and might be even highly biased depending on the details. Okay, so imitation, so we kind of map the spectrum of imitation along kind of when we don't see the context. Now let's assume we get the reward. We're not just trying to imitate, but we're acting in the world, and we have this offline data as an aid, which is more similar to what we did in the Bandit case. Now we have this offline data. We're not trying to purely imitate it. We can act in the world. We don't have to use this offline data, but we want to use it to get better. And what we might want to try is just to regularize. So what we see here is on the left side is just maximizing reward. We can do that. We're playing online. We don't have to use the offline data. And the right term is a regularization term, where DF is some F divergence, whatever, total variation distance or whatever, between the traces that we see in our policy versus the traces that the experts found. We say, okay, we know the expert acted optimally, so let's try to mimic them. We can show this is biased, and we can't even calculate this because we don't know the expert distribution over the context. But we kind of developed a slightly more involved optimization problem, which I regretfully will not go into the details, which we show is actually unbiased. And it has this kind of GAN flavor where we use, it's not a GAN, but where we learn kind of to generate the trajectories, and then we have, that's the G, and then we have this kind of, that's a generator, and this is the discriminator saying, okay, they need to be similar, but we're not sensitive to this, and we can show that we will actually converge this can be solved, and this is not biased. We will get to the optimal policy eventually. And we have kind of two algorithms for this, one which is provably convergent, but is kind of slow and impractical, one which is gradient based. It's a non-convex objective, so it can't prove anything, but it actually works. So I'll skip the algorithm. And I'll just describe like one experiment we did. So here we have weaker theoretical guarantees. We don't have like impossibility or impossibility results. We haven't proven that we converge faster, but we will see that we do in practice, at least. We would like to prove more, but we haven't done that yet. And I'll show one experiment using something called the assistive gym environment from Erickson et al., where it's basically a robot trying to take care of someone, feeding them, dressing them, bathing them, helping them drink, etc. The state is like the robot and person state, that's the state. And the context is the person's weight, height, and gender and disability, and their own preferences on how they'd like to be helped. And the action state is the joint forces for the robot. And the reward is success in the task plus these user preferences. Now, we don't have an expert here. We trained an expert on some dense reward. So we basically built this dense reward function based on like understanding the task that helps the expert learn much better. But then our model learns using the sparse original reward, which is much more challenging. And we changed the context, like all these weights, heights, and so on, with just some probability beta. And what we see, this is an example of what the agent learned. What we see here is that the dashed lines are without our, like, kind of this algorithm we developed, which tries to use the offline data. And the solid lines are using it. So we see we get a better performance over time, though it does not match the expert. The dashed line RL is just using RL with no prior data. And we have this kind of for various tasks. And in general, we see that our CTS method, corrective trajectory sampling, does perform better. Just this is how it looks like with like a large value of beta, so a large degree of covariance shift. On the left, it basically fails. It doesn't manage to help address this person, which is different, like again, different in their characteristics compared to the offline data. With sample correction, it manages. So it gets, and it managed to learn, the offline data helped it learn how to do this task correctly. Okay. So just to summarize, and I'm sorry I didn't go into all the details of the algorithms. I'm happy to talk about them offline. There's a lot of kind of cool math stuff going on there, which I haven't gotten into. Offline data might make online learning more efficient. That's pretty obvious. But often offline data does not match online data. There's like a lot of discrepancies that we have to think about if we're actually trying to do this in the real world. And we're kind of mapping some of the failure modes and necessary conditions for success. We looked at partial observability and distribution shifts specifically. In linear bandits, we saw that offline data plus the ability to sample from the offline policy sometimes allows us to accelerate online learning, depending on kind of how nice the partial observability is. But it doesn't have to be super nice, just it doesn't have to be super nasty. And in imitation learning, so where we're trying to learn to act like an expert, but things change, the context change, the answer is it depends on the details of how the context affects the problem. And we map this kind of spectrum of like possibility and impossibility. And then we said, okay, if we have expert data and we're actually working online with the reward, we're not just trying to imitate the expert, we're trying to learn on our own but we have this expert in the background trying to help us. We have an algorithm which show empirically has accelerated convergence. We can prove that it doesn't harm, but we haven't yet proved that the accelerated convergence is provably accelerated. We only showed it in like a couple of experiments. I showed you just one example. Okay, I just want to thank the people who did this work, Guy, and most of all, Guy Tenhold. So these two papers are part of his PhD. He's now finishing his PhD thesis, and he's a great student, and I'm sure we will all hear more of him in the future. And that's it. Thank you very much for your time, and I'm happy to take any questions or start with the discussion.
Thank you very much, Uri. So we'll start with the discussion and have all the questions just to everyone. So Frederick, yes, so if you could go with a chair here in front. Now we're having an experiment.